Hello, today we're going to review Unit 9 for the AP Chemistry exam. This is everything to do with thermodynamics and electrochemistry, and we're going to do some free response and some multiple choice questions. Okay, so we've got two possible Lewis electron dot diagrams. Explain why the diagram on the left is the better representation, justify it based on formal charges. So this is a Unit 2 question. So formal charges, it's always the number of valence electrons it normally has minus the valence electrons currently assigned to it. So you would do, for current assignments, you count each lone pair, you count each electron once, and then for each bond you only count one electron because we're assigning it, so one to one of the atoms in the bond and one to the other atom in the bond. So let's go ahead and do that. Hydrogen normally has one valence electron, carbon normally has 4, nitrogen normally has 5, oxygen normally has 6. 1, 4, 5, 6. But now let's do how many are currently assigned to it. Hydrogen has 1 assigned to it currently, just 1 for the bond. Carbon has 4 bonds, 4 electrons assigned to it. Nitrogen has 4 bonds, so 4 electrons. And oxygen has 1 bond plus 7 electrons. Plus 6 electrons in the lone pairs, so 7 total. So that means hydrogen's lone pair is, or formal charge is 0, carbon's is 0, nitrogen is +1, oxygen is -1. On this side, I've got just 1 bond for hydrogen. I have 3 bonds and 2 electrons in a lone pair, so that's 5 for carbon, 4 bonds in nitrogen, and 4 electrons plus 2 bonds is 6 for oxygen. So I have 0 for hydrogen, -1 for carbon, +1 for nitrogen, and 0 for oxygen. So they already told us the left one is better. But the reason why is that it puts the more negative formal charge on the more electronegative atom. So oxygen has a much greater electronegativity than carbon or nitrogen. And because of that, it wants to have that negative formal charge, or more likely to have that negative formal charge compared to the carbon having it on the other structure. Okay, so fulminic acid can convert to isocyanic acid according to that equation using the electron dot diagrams and the table of average bond enthalpies determine the value of delta H for the reaction. So bond enthalpies is kind of Unit 6. It's going to be bonds broken minus bonds formed. So the broken ones are the reactants, and it looks like we're breaking basically everything, and that's fine because if you're not sure like what's breaking and what's forming, just assume everything breaks and everything forms again. It'll be the same answer either way. So let's go ahead. We'll break 1 carbon-hydrogen single bond, which is 413, and we'll break a carbon-nitrogen triple bond, which is 891, and we'll break a nitrogen-oxygen single bond, which is 201, and we'll subtract our bonds formed, hydrogen-nitrogen single bond, which is 391, our nitrogen-carbon double bond, which is 615, our carbon-oxygen double bond, which is 745. So when we multiply, or when we add and then subtract, we get -246, and that's kilojoules per mole of reaction. And that's our final answer for B. So a student claims that delta S for that reaction is close to 0. Explain why the student's claim is accurate. So you were going from just one isomer to another isomer. They have the same number of molecules of both, same state of matter. They're just rearranging how the atoms are organized. So that's why it's close to 0, because the entropy of the reactants and products are both very similar. So the change in entropy is close to 0. And that was just one point. For part D, which species, fulminic acid or isocyanic acid, is present at higher concentration at equilibrium? We can use the equation delta G equals delta H minus T delta S. Because we said delta S is essentially close to 0, that this term will have very little effect on the overall. So, and we found delta H in our bond enthalpies. That was negative 246 kilojoules per mole. So we can assume that delta G will also be very close to negative 246 kilojoules. So that's negative, so that is thermodynamically favorable in the forward direction. Because it's thermodynamically favorable in the forward direction, that means K is greater than 1, and so it will favor the products, and you'll have more of the isocyanic acid. Now that question was 2 points. One for choosing the isocyanic acid by saying that delta G is most likely negative, and then the second point was for indicating that because delta G was negative, K is going to be greater than 1. And you had to do both because it says and the equilibrium constant. Okay, so we have urea decomposing into ammonium and the OCN negative here. This decomposition reaction, we have the time and the concentration, and the student proposes that the rate law is rate equals K times that, and explain how the data support the student's proposed rate law. This is a Unit 5 question, but it's nestled in with the Unit 9 stuff. You'll see more and more that they mix questions from different units together. So I always notice when I see rate laws like this that this is a first order rate law. And when you have a first order rate law, it's worth checking half-life. Okay, so if we're starting at 0.1 and it goes down to 0.5, okay, that took 10 hours. If I go from 0.5 down to 2.5, that's another 10 hours. If it's the same amount of time, then yes, it's a first order reaction. So as long as if half-life is constant, yes, it's first order. Now, if you wanted to, you could have taken the natural log of all of those concentrations and shown that it was a linear relationship between time and the natural log. That's fine. You just didn't need to use all of that effort. Use half-life. Whenever you're concerned about first order, think about half-life. Okay, so using the proposed rate law and the student results, determine the value of the rate constant K and include units. So let me rewrite the rate law. Rate equals K times CO NH22. I'm going to go ahead and say it because it's first order, right? It's going to be easier to find the rate constant K by using the half-life, because the time for one half-life is equal to 0.693 over K, and that's on your formula sheet. So the time for one half-life is 10 hours. And then if I go ahead and solve for K, I get K is equal to 0.0693, and the unit then for that would be inverse hours, because we're moving that to the bottom, hours -1. And so you had to have the units correct and the value for K correct. If you really wanted to, you could have converted it all to seconds and then find K, but I think that's more difficult. You could just leave it in hours. Yeah. So for part F, the student learns that the decomposition reaction was run in a solution with a pH of 13. Describe an experiment, including initial conditions that you would change and the data that you would gather to determine whether the rate of the reaction depends on the concentration of OH negative. Whether the rate of reaction depends on the concentration of OH negative. So really all you needed to do is repeat the experiment from before and change only the hydroxide concentration and measure the concentration over time, just like you did in the first experiment. But by only changing this one thing, you'll be able to accurately compare the two experiments to see if there is effect. You could have said, multiple different concentrations, that's fine, but the key here was noticing that this should be the only thing that is different, the concentration of the OH negative. Okay, so here's another free response question. We have an experimental setup for an electrochemical cell that contains 2 standard half cells. We know it's voltaic because there's no power source. And then they give us the equation for that reaction, which is nice. Identify M and M2+ in the diagram and specify the initial concentration for M2+. So we know that the electrons are traveling from M to X. So in this case, the zinc is going from a 0 to a positive 2. So the zinc is losing its electrons. That means M, it must be zinc, and the X must be the nickel. So identify M and M2 plus. So zinc and zinc 2 plus ions. And specify the initial concentration for M2 plus in the solution. Well, we want it to be, because, it says it's a standard half cell. That's the key. When you have standard conditions for electrochemistry, it's always 1 molar conditions. And so that was 2 points, 1 for getting the correct identity and 1 for getting the correct concentration. Okay, so remember we said M was zinc and X must be the nickel. And it says indicate which of the metals electrodes is the cathode. So reduction happens at the cathode, and reduction is gaining electrons. So the nickel ions are gaining electrons to become solid nickel, so that means this one must be the cathode. And then we need to write the balanced equation for the reaction that occurs in the half cell containing the cathode. So we just want to pull out just the nickel part here. Nickel 2 plus 2 electrons will give us solid nickel with no charge. And I know it has 2 electrons because you're going from a +2 charge to neutral. Okay, so now for part C, what would the effect on the cell voltage be if the concentration of zinc was reduced to 0.1 in the half cell containing the zinc electrode? This is the Nernst equation. So I need to find Q. It's always products over reactants. So we have our zinc ion concentration all over the nickel ion concentration. Normally, this ratio would be 1 because you have 1 molar solutions in standard conditions. But we have a non-standard condition here. The zinc was reduced to 0.1 over the 1 for the nickel. So I get that Q is equal to 0.1. So because Q is less than the standard for K, Q is too small. I need to make Q bigger. I make Q bigger by increasing the products. So it's going to shift towards the product side and make the forward reaction happen more, which will increase the cell voltage. Now you could calculate that using the Nernst equation, which is the cell potential is equal to the standard cell potential. Actually, I don't know that they gave you the standard cell potential. So no, you couldn't actually calculate it. If you had the standard cell potential, then you could use the Nernst equation. But for this question, it winds up not being important because they don't give us all the information we need. So cell voltage increases because the forward reaction happens more. D, describe what would happen to the cell voltage if the salt bridge was removed. The reaction would stop. The cell voltage would go down to 0. The salt bridge is important because it regenerates the charge balance for your cell. So we said this one was the cathode with the nickel ions, and zinc was must be our anode then. In our salt bridge, anions, negative ions, travel toward the anode to replenish the negative charges, and positive ions travel toward the cathode to cancel out the extra electron charges. So if you don't have the salt bridge there, it winds up an unbalanced charge and the reaction would stop. Okay, let's do a few multiple choice questions. We have a voltaic cell. We know it's voltaic because there's no power source, and it is a spontaneous reaction then. And we have 2 molar cadmium nitrate added to the left beaker. Okay, so this is an application of non-standard conditions. We are increasing the cadmium nitrate instead of being 1 molar. The spontaneous reaction that occurs is here, and so I'm increasing the cadmium, so that means for Q, Q is the cadmium on the top, the silver ions on the bottom, squared because of the 2. Normally that would be 1, but now I am increasing the top, so making Q larger than K because it's greater than 1. And when Q is too big, I need to make it smaller to reach equilibrium, so it will be, it will shift in the reverse direction. to reach equilibrium. So voltage will decrease until equilibrium is reached again. It does not become zero and remain zero. It definitely changes because you're changing the concentration. So yeah, it's got to be B. Okay, standard reduction potentials they give us in the table. What is the value of our cell potential for a standard galvanic cell? That means it's spontaneous. And when you see that, you know that the one with the smaller one must be changed to be oxidized, and this one will stay and be reduced. So whichever one is smaller needs to flip, and we're going to flip it to be CR3 plus 3 electrons, and it becomes positive 0.41. Just a side note, remember when you manipulate a reaction, if you multiply it by something, you do not change the value of the cell potential. Only if you flip the reaction can you flip the sign, but the actual magnitude does not change. So then I can go ahead and just add those together, and I get 1.21 as my overall voltage. And finally, here's a thermodynamic multiple choice question. The largest decrease in entropy. So it's getting more organized. It can't be A. A is increasing in entropy because you're going from one solid and splitting up into a solid and a gas. B is going from 3 particles of gas to 2 particles of gas, so maybe. C is going from 3 particles of a solid to 3 particles of solid. I'm guessing that one's probably not it because there's no way for us to tell based on the structures. For D, we have 6 molecules of gas going to 7 molecules of gas. It's getting more entropy. And for E, we're going from a solid and a gas and 7 particles to 2 particles of a solid. So I'm going to guess that it is E is the best answer here because you're going from gas to solid, but you're also going from lots of particles down to only 2 particles. So your decrease in entropy there is most likely greater because of that larger difference between the reactants and the products.